Hello, this is an introduction or maybe more of a brush up in basic concepts of linear algebra. This lecture is part of the Quantitative Methods in Herd Management course at the University of Copenhagen, but also of different workshops provided by the section of Production, Nutrition and Health. So this is an outline of how this lecture will go. We'll start with a simple concept of what is algebra, then talk about solving equations, and then move on to talk more at length about matrices, going into types of matrix, matrix operations, which is the main focus of this lecture. Then systems of linear equations, and finally how all of this connects to state space models, or more specific dynamic linear models, which is our main objective here. The exercises and some of the examples here come from the book Herd Management Science 2, which you can find at this link if you don't already have it. So let's start talking not about algebra, but about arithmetic, since it is a simpler concept and which people are more immediately familiar with when they think mathematics. So it comes from the Greek arithmos, which means to count, and it involves computations of known numbers, using, for example, the four basic operations. So an example of an arithmetic expression would be 7 plus 3 equals 3 plus 7. And one important characteristic here is that this expression is only true for the values presented. So if you lose, hide, or switch one of these values, then this expression is no longer true. Algebra, on the other hand, comes from the Arabic algebra, meaning the reunion of broken parts. So it allows you to combine unknown quantities with numbers and uses a set of generalizable rules to solve problems. So an example of an algebraic equation is a plus b equals b plus a. And this expression is always true for whatever values a and b might take, whether they are known or not. So it's more of a framework for problem solving than a calculation discipline, really. So now I would like to tell you a story about equations. And it starts with Old MacDonald had a farm. So if you are familiar with that one, you know that on his farm he had some sheep. But he's Old MacDonald, so he can't really remember exactly how many sheep. So let's call the number of sheep in his farm x1. We also know that on his farm he had some geese. But he also forgot how many. So let's call that number x2. And things have changed since the song was written, and self-sustaining family farms with a bit of everything are almost extinct now, so he has no other animals. But with his keen eye for detail and his bad long-distance vision, he could still count the number of heads in his yard, which was 25. And he knows that both sheep and geese have only one head each, so he sets up the following equation: 1x1 plus 1x2 equals 25 for the number of heads. Now, he also knows, he was also able to count the number of legs, and it was 70. So we know that each sheep has 4 legs and each goose has 2. So we can also write that in an equation as well. So 4x1 plus 2x2 will give us 70. So now our whole McDonald's situation can be described by two equations with two unknowns. And both equations describe the same two unknowns. So when we have several linear equations describing the same variables, we call it a system of linear equations. And that's all nice and well as far as we wanted to use equations to describe a problem, but I've mentioned earlier that algebra was a framework for solving problems. So how do we go about solving equations and consequently solving our old MacDonald problem? So this is probably something you'll remember from school, but let A be different from 0 and B be known real numbers. So both of them are known real numbers, and A is different from 0, and X is an unknown real number. So if for some reason we know that A times X equals B, we say that we have an equation, which is exactly our situation here. So we can solve the equation by saying if A times X equals B, we find the value of X by dividing B with A, which is the same as doing A to the power of minus 1 times B. So we go back to our slide showing two equations with two unknowns. We could solve them by substitution, which is what we are mostly used to do. And we do that by looking at, for example, the second equation, and then we solve x2 in terms of x1. So we get that x2 equals 70 minus 4x1 divided by 2, which will then give us 35 minus 2x1. So I take that value and I plug it in the first equation in the place of x2. So suddenly I know that 1x1 plus 35 minus 2x1 gives us 25. So if we solve that, we keep solving, we find a value of 10 for x1, and then a value of, then we take that value of 1, replace it in the first equation again for x1, and then we obtain a value of 15 for x2, meaning 10 sheep and 15 geese in Old MacDonald's farm. But could we solve this problem using matrices instead? So you'll probably instinctively know that in a lecture focused on matrices, the answer must be yes. But why would we want to do that if we are so used to working with substitution? Well, because matrices enables us to express very complex relations in a very compact way. It also enables us to solve large systems of linear equations. And in our example here, it doesn't really look like a big problem because we only have two variables and two equations. But picture airplane aerodynamics equations, for example, with hundreds of variables and thousands of equations to be solved at the same time for optimization. But to start going in that direction, we first need to remember what is a matrix. So if we consider our old MacDonald's system here, we can write the values of x1 and x2 in matrix form. So on the first row, we have the values for x1. So 1 plus 1 x1 and then plus 1 x2, so 1 and 1. And then on the second row, we write the values for x1 and x2 in the second equation. So we have 4 and 2. And so we have the values for x1 here and the values for x2 here. And that makes for a 2 by 2 matrix, where the official notation for that is the number of rows by the number of columns. So we have 2 rows, we have 2 columns, so it's a 2 by 2 matrix. So this actually allows us to express the known part of those variables in a very compact way. So that was a 2 by 2 matrix, but imagine if we had more equations or more variables. We could also have a 2 by 3 matrix or a 3 by 2 matrix, for example. See, 2 rows, 3 columns on the first, and 3 rows, 2 columns on the second. So the notation is still rows by columns. And because of that notation, we can express any position in any matrix symbolically like this. So each value has the matrix name, followed by an index composed by the row number and then the column number. So the first value on matrix A is A11 because it is sitting on the first row, first column in matrix A. The last value in matrix A is A23 because it is sitting on row 2, column 3. And the same logic applies to matrix B down there. Now we have different types of matrices depending on their dimensions. So some of them are important to remember for you to understand the terminology when reading about models and the models that use them. So a matrix with dimensions n times n, that is a matrix which has the same number of rows as columns, is called a quadratic or rectangular matrix. A matrix with dimensions 1 times n, meaning a matrix that can have many columns but only one row, is called a row vector. And finally, a matrix with whatever number of rows but with just one column is called a column vector. We will now start to delve a bit more into the wonderful world of matrix operations. So starting with the most basic one, which is addition. Two real numbers can always be added together, no matter what. But can the same be said for matrices? And if you're looking at the slide, you know that the answer is no. So two matrices can only be added if they have the same dimensions, because the resulting matrix from the sum of A and B will have for position 1, 1, the sum of A1, 1 and B1, 1. On the same row, second column, it will have the sum of A1, 2 and B1, 2, and so on and so forth. But that also means that a real number can never be added to a matrix, unless that matrix has dimensions 1 by 1. So you should be aware that if you type in that operation in R, for example, 5 plus matrix A, it will do it by adding 5 to each value in the matrix. And that's just wrong. So remember that. And from the axioms of real numbers, it follows that for two matrices A and B that can be summed, A plus B is equal to B plus A. So the commutative law applies here. Also, every matrix n by m has a zero element, so that for matrix A, A plus 0 equals A. So what does that element look like? Oh, it follows logically enough that this element is a matrix with the same dimensions as A, in this case a 3 by 3 matrix. But it should be populated only with zeros. And that is known as a null matrix or zero matrix. And it's also the additive identity matrix. And there is also something called the additive inverse, that for every matrix A, the sum with its additive inverse B will result in the zero matrix. So that element will be a matrix with the same dimensions as A, but populated with the additive inverse values of A, meaning the same values as A, but with a negative sign applied to them. And although we haven't been doing this very long now, this will still be a good time for you to take a 5-minute break, because we are going to change the direction a little bit, even though in the same subject. Now we're going to continue with matrix operations, but we're going to do something slightly more complicated. So it's a good time to pause the video, cool your head a little bit, find the link in the comments to the video so you can do some short meditation if you want, or just get some rest, take a walk. Welcome back. So now take a deep breath and a sip of your favorite algebra learning drink, because we are going into matrix multiplication, and the rules are a bit different from what we just saw for addition. So let's start with the rules. Two matrices, A and B, can only be multiplied if A has the same number of columns as B has rows. So here we have matrix A, which is a 3 by 3 matrix, 3 rows, 3 columns. And we have matrix B, which is a 3 by 2 matrix. So it has 3 rows, 2 columns. So in this case, I can multiply A and B because A has 3 columns and B has 3 rows. So why does it have to be like that? Because, as the text says here, an element of the product is calculated as the product of a row and a column. Now, what does that mean in practical terms? So let's start here. If I'm going to multiply this matrix A with this matrix B, I start by taking the first row in A and the first column in B, as marked in red. This will give me the value for the first position in the A times B resulting matrix in position 1, 1, marked here in green. So I'm going to take the first value here, in this case 2, and multiply with the first value here in B, which is a 5. And I'll keep that result here for now, because we are going to add that with 3 times 3, and then with 2 times 1, which gives us 21. And that is the value of position 1, 1 in our resulting matrix. So now we move on to position 1, 2, which is the second column of the first row up here. So to do that, we stay on the first row of matrix A, and then we do the sum of the products with column 2 in matrix B, in the same way we did before. So that's going to be 2 times 4 plus 3 times 6 plus 2 times 2, which should give us 30. So with that, we are done with the first row in the resulting matrix, and we move on to the next row. To do that, we take the second row in matrix A and multiply it with the first column in B again, like we did before. So that gives us a value of 15 for this position, because it's 1 times 5 plus 2 times 3 plus 4 times 1. And if we just follow the same process, we get 24, 22, and 26 for the other positions. So feel free to pause the video and do the calculations for the last 3 values yourself if you would like. That's a good exercise. Why not? So in the beginning, it may be a bit difficult to remember which dimensions from which matrix needs to match with what. So of course we have a trick for that, right? So this text box here has a general formula for the dimensions of two matrices A and B, with R denoting the number of rows and C the number of columns in A and B, right? So two matrices may be multiplied if the two numbers in the middle match. And if you want a quick check on whether you did it right, the resulting matrix should have as dimensions the two numbers on the outside. So for our case, matrix A is 3 plus 3, and matrix B is 3 by 3, and matrix B is 3 by 2. So the two middle numbers match because they're both 3. And the resulting matrix, as we can see, has 3 rows, 1, 2, 3, and 2 columns, 1, 2, which are the dimensions on the outside, marked in green now. So let's go over the process again. First, we check the dimensions to see if the two in the middle match, and they do, because A is 3 by 3 and B is 3 by 2. Then we take the first row in matrix A, first column in B, and we do the sums of the products. 2 times 5 plus 3 times 3 plus 2 times 1, and we get 21. Then we stay with the first row in A, but then we take the second column in B, and we do 2 times 4 plus 3 times 6 plus 2 times 2, and we get 30. Then we move down to the second row in matrix A, back to the first column in matrix B, and we have 1 times 5 plus 2 times 3 plus 4 times 1, which gives us 15. And again, if we keep doing that, we get again 24, 22, and 26. Then we check the dimensions of the resulting matrix, boom, green, and they seem to be right, because the resulting matrix is a 3 by 2 matrix, and those are also the numbers on the outside here. If you need to go over the process again, stop the video, go back to the previous slide as many times as you feel necessary, as we are going to use those concepts to go a bit deeper. So now we also need to talk about some properties of matrix multiplication, because they are different from the properties of matrix addition. So here, for example, I would like to know what are the values in a matrix I'm calling I1, such that any other matrix A, when multiplied by I1, returns the same original matrix A. So I'm looking for a multiplicative identity for matrices, right? So I'm giving you here a matrix A with these 3 numbers, and I'm going to give you a hint that, in order to get the 2 here, for example, I would need to multiply this 2 with 1, and then the minus 1, add it to a minus 1 multiplied with 0, for example, and then add it to the 15 multiplied with 0 again, because then I get only the 2 as return. So you should pause your video here, try to figure that out for yourself. You can copy down matrix A on paper, try your newly gained knowledge on matrix multiplication, or you can also do the multiplications in R if you already know how to do it. So think about it, try different values and dimensions for matrix I1. So these are the decomposed matrix multiplications that need to happen in order for our operation to result in matrix A. As I mentioned, you will need to multiply 2 with a 1, sum it to a minus 1 times 0, sum it with 15 times 0. So we get 2 here. Now, in order for me to get minus 1 here, I need to multiply the 2 with a 0, the minus 1 with a 1, and the 15 with a 0 again, and so on and so forth. So this is what this matrix looks like. I hope you have obtained the same one when trying to get it yourself. So since we were talking about the multiplicative identity, so this means that this matrix we obtain here is what is called the identity matrix. So an identity matrix is a quadratic matrix, so it has the same number of rows and columns. It contains ones in the main diagonal and zeros on the rest. And then n must match one of the dimensions in matrix A. Now we also have a multiplication commutative property, but unlike for real numbers, when multiplying matrices, A times B is not the same as B times A most of the time. So the commutative law normally does not apply to matrices, as it applies to real numbers. So now here you have another opportunity to practice your newly acquired matrix multiplication skills. So you can go on and try to solve these operations to check if A times B is the same as B times A for these two sets of matrices. So you should pause the video while solving them, as I will show the solutions in a bit. So as you can see here, A times B did not yield the same as B times A for the first set of matrices. So we just inverted the order here, A times B, B times A, and the result is completely different. And now for the second set of matrices, one of them isn't even doable because the dimensions here do not match, right? A has 2 columns and B has 3 rows. So you cannot do it. So the commutative law did not apply to these matrices. But, as usual, there are exceptions. So the commutative property does not apply to matrix multiplication except for identical quadratic matrices, identity matrices, or a zero matrix, which I mentioned before is a matrix completely populated by zeros. So we can see very easily in this example why the commutative property works for identical quadratic matrices. It doesn't matter which one of them comes first, the results will be the same. And because they are quadratic, the number of rows and columns will always match. But we can also see that if they were not quadratic, so for example, if it was a 2 by 3 matrix, the middle numbers wouldn't match, meaning that you couldn't even multiply them. So let's take a look at the other two exceptions, identity matrix and zero matrix, to verify if the commutative law applies to them. Here we have a matrix A being multiplied with its identity matrix as A times I, and then as I times A. And below we have matrix A being multiplied with a zero matrix Z as A times Z, and then Z times A. So please take some time to verify by hand if the commutative law applies in these cases, and you should pause the video while you do it. As we can see, A times I produces the same as I times A. And it's quite straightforward that any multiplication with a zero matrix has another zero matrix as a result. So it is illustrated that the commutative law does not apply to matrix multiplication except for identical quadratic matrices, identity matrices, or a zero matrix. Now there are also other operations that can be done to matrices. And we will show two of the simpler ones here, and we'll come back with the others later. So the first one is that any real number R can be multiplied with a matrix. And the way to do that is to just multiply the number with each position on the matrix. So 2 times 1 gives us 2, and then 2 times 2 gives us 4, 2 times 3 gives us 6, 2 times 4 gives us 8, and so on. Now you may be asking yourself, how come I cannot sum a real number with a matrix, but I'm allowed to multiply it? Well, that's because when you sum a number with a matrix, you are basically adding a 1 by 1 matrix to a matrix with other dimensions. And we already learned here that you cannot do that. However, when you multiply a number with a matrix, what you're doing is to sum a matrix with itself as many times as the number indicates. And then, of course, the matrices being summed all have the same dimensions because they are the same, and so that's okay. Moving on, the transpose of a matrix is formed by changing the columns to rows and is often called a T or a line to say that it is the transpose of matrix A, for example. It is formed by changing the columns to rows. So in this case here, we have the transpose of A at the bottom now. First column in A became the first row in A line, and the second column in A became the second row in A line, or A transposed, as we like to call it. Well, it's time for some exercises now. So this is exercise C11 from the book I listed in the beginning. So you can, of course, do everything by hand, but the idea here is that you implement these operations in R. So since for some this will be their first contact with using matrices in R, I have added a cheat sheet with some coding hints. So the first 2 hints teach you how to create a matrix in R, and in this case already gives you the value, so you could in principle just copy and paste. Sums are quite straightforward, but for multiplications you need to put the star or asterisk between percents, otherwise R just multiplies each position with its corresponding or returns an error if the dimensions are non-compatible. So transposition is also an easy one, and you don't need to worry about determinants or inversions for now. So if you finish quick and want to practice some more, you can return the video to the slide where we tested the commutative property for matrix multiplication and implement those operations in R, for example. So if you're ready to start, you should pause now as you do the exercises in R, and after them we'll have a 5-minute break. So you can cool your head a little bit or try some of the 5-minute meditation from the link on the next slides and on the comments to this lecture. We are back with more matrix operations and some interesting ones at that. So the inverse of a matrix, in this case a multiplicative inverse. So for every real number x, there is 1 divided by x, for which x times 1 divided by x returns 1. That's quite straightforward. We can also write 1 divided by x as x to the power of minus 1, where x multiplied by x to the power of minus 1 also gives us 1. So does every matrix that are non-zero have a multiplicative inverse B such that A times B returns the identity matrix, which is our matrix corresponded to the number 1 in multiplication? Well, that element will exist only if matrix A is quadratic, so like 2 by 2, 3 by 3, etc. And matrix A is non-singular, meaning that its determinant is different from 0. In any case, the inverse of A is always A to the power of minus 1, not 1 divided by A, because you cannot divide by a matrix. So the inverse of a matrix is always the matrix to the power of minus 1, not 1 divided by it. But how do we invert a matrix? It depends a little bit on the dimensions. So here is a good example for a 2 by 2 matrix A. So the determinant, the inverse, will be equal to 1 divided by the determinant of this matrix and multiplied with its adjugate matrix. So the adjugate matrix of A is obtained by switching positions for the components of the main diagonal. So here A11 and A12 and A22 change positions. And then we take the negative of the components of the secondary diagonal in their original positions. Now, the determinant of a matrix is a real number, and therefore you can divide 1 by it. That's why you cannot invert singular matrices, because you cannot divide by 0 if this determinant here was 0. So for a 2 by 2 matrix, we obtain the determinant by multiplying the components of the main diagonal and then subtracting the product of the secondary diagonal. So if we plug some values in our generic example, we get the adjugate matrix by switching positions between the 1 and 0, and then adding negative signs to the 2 and 3. We get the determinant of this matrix by doing 1 times 0, which is 0, minus 2 times 3, which is 6. So the determinant is minus 6. Then we have 1 divided by minus 6 multiplied with the adjugate matrix. And that gives us the inverse of matrix A, which is this beautiful thing here on the right side. But that's not something that you have to do by hand, and it was actually not that complicated, was it? So it is not the objective of this lecture that you should learn how to calculate determinants for more complicated matrices, and it can get quite worksome. The main point here in this part of the lecture being to invert a matrix is not the same as to divide 1 by it, because you cannot divide by a matrix, and you should remember that, please. We have a few more exercises here where you get the chance to implement matrix inversions and determinant calculations in R, as well as to check if the assumption that a matrix A multiplied by its inverse results in the identity matrix. So the cheat sheet is there to be used, and you should pause the video while you do them. But now that you've learned a lot about matrices and how to do operations with them, we can go all the way back to slide 5, where we started this conversation, right? So remember we had set up two equations with two unknowns in the old McDonald's system of linear equations. So we solved them earlier using substitution, but now we want to solve them using matrices. So we start by writing the whole equation in matrix form. On the first time, we had only stored the values for the unknown variables. Now we wrote the whole equation as a matrix. So you can see that this works if you remember the rules of matrix multiplication. So if we multiply these two terms here, we will have 1 times x1 plus 1 times x2. That's how matrix multiplication works, and that's exactly what is written up here in green. Because the two formats are just different ways of describing the same relationships. And now you know why you write it like that and how to solve it. So let's look at that last part, how to solve it. So now that we have our old McDonald's matrix equations and we have our equation solving framework here, the a times x equals b, therefore x equals a to the power of minus 1 times b. So we just need to put the two things together, right? So we define the bits of our equation as a, x, and b. And there it is. So this first part here at the top left, now it's true, isn't it? We just added names to the parts. So then we can pull that last bit of info from the top right to solve it. So, matrix A, x equals matrix A to the power of minus 1 multiplied with matrix B. And that would mean the inverse of matrix A multiplied by B. Now, the good thing is this solution is valid whether if it's a system of two equations or a million equations, because all your variables and all your equations describing them are going to be contained in those three matrices, no matter how big your equations or your system are. So if we implement that in R, as we do, because we don't need to do it by hand, we have our little cheat sheet here with the code. And if you do that, you can pause and try it and then come back. But in principle, where we get from it is a column vector, x, containing the values 10 on the first row and 15 on the second, which means 10 sheep and 15 geese, because x1 was the number of sheep and x2 was the number of geese. So this is the same result as we got from solving it by substitution, if you remember it. But we could easily have 10 variables instead of 2, and this way we don't need to go back and forth to solve and substitute each one of them. So now that you've learned about what are matrices, how to do operations with them, and how to solve matrix-based equations, we finally get to the point where all of that connects with the main point of the course you're following or is about to follow. So what's the relation between matrices and state space models? So let's look into that. Let's start by assuming that old MacDonald also decided to get some dairy cows. So the average yield per cow on the first day in milking is 28 kilos. So we have here DIM, which means days in milking, and variable y for milk yield. And y1, therefore, is the yield on the first day in milking, the first day of lactation on average in that herd. So based on Wood's lactation curve, we expect an increase of about 0.2 kilos per day during the first 60 days. With that information, how can I model the yield on the upcoming days for a random cow? Well, we use state space models precisely for that. We use them to describe a present state and how that state is expected to change given a change in time units. In our case, we are using a specific type of state space model called a dynamic linear model, or DLM. So the yield on day 1, which is our present state, was 28, and our expected change for the next time step was an increase of 0.2. So we can define a parameter that we call theta, containing that information, and theta will be a matrix, or more specifically in this case, a column vector. We call it theta 1 because it describes the state and the change on day 1. Now, dynamic linear models consist of two equations, the observation equation and the system equation. So the observation equation estimates the answer to your question. So in this case, what is the milk yield on day 2? So that's why it says y2 before the equal sign. While the system equation describes how the system changes or evolves over time. So each one of those equations uses a special type of matrix to fulfill their function, which we will learn more about in the modeling lectures. But for now, the transpose design matrix F is used in the observation equation, and the system matrix G is used in the system equation. You will soon understand why each one of them looks like they do. So V and W in the equations are variance components of each equation, about which you will also learn more further on in this course, but for now, it is enough to understand that they represent our uncertainty about the observed values in the first equation and about how the system behaves in the second. So for practical purposes in this lecture, we will just ignore them for now. Therefore, although the observation equation is always described first, when using them, you start with the system equation, because you need to calculate the change over time before obtaining your final estimate. And that's actually easy to remember, because if you look at the two equations, in order to use the observation equation, you need F transposed, theta 2, and V, but we don't have theta 2 yet. On the other hand, for the system equation, we need the system matrix G, theta 1, and W. And considering that we chose to ignore W, we actually have everything we need for this one, and then we estimate theta 2 to use it on the observation equation. So you may recognize the shape of this table we put down there, this square thing, because it looks very much like our matrix multiplication slide, because that's exactly what it is. So we have our system equation on the top right there, so we don't forget what it looks like. And then we just substitute theta 1 and the G matrix with the values we have for them. So it is very important that they keep the order in which they appear in the equation, because as you remember, the commutative property most often does not apply to matrix multiplication. So we start by multiplying the first row in G with the first column in theta 1. So that's 1 times 28 plus 1 times 0.2, which gives us 28.2. Then we move to the second row in G, where we have 0 times 28, which gives us 0, plus 1 times 0.2, which is 0.2. So my theta 2, which is my parameter matrix describing the current state as at day 2, or at least what I expect it to be, will have the updated milk yield 28.2, plus the expected change on the next day, which we assume to stay constant for the first 60 days at 0.2. Plus the uncertainty W, which we will not deal with right now. And now that we have theta 2, we can actually use the observation equation. We have our cheat sheet up there on the right telling us to multiply the transpose of matrix F with theta 2. And by doing matrix multiplication, we get 1 times 28.2 plus 0 times 0.2, and that is 28.2. So we use this equation to extract the actual prediction for milk yield on the IM2 from inside the parameter theta. So it can be used as a regular number for error estimations and so on, and to actually answer the question, what do we expect the milk yield on day 2 to be for any random cow in Old MacDonald's farm? And the answer is 28.2, again, plus some error. So although the milk yield example was very illustrative and useful, it is also very simple. It only uses one variable, and it assumes a linear trend of 0.2, which only allows us to make predictions for roughly the first 60 days if we are to follow a classic lactation curve. But we can use dynamic linear models to make more complex predictions. So in this slide, we are trying to model the water drinking patterns of fattening pigs. So the curve repeats the same pattern every day, with a small secondary peak around 10 in the morning, a main peak around 12, and then it goes down to very little consumption during the night. And then it starts again on the next day. So there is a complex pattern to model if you are making predictions per hour. And not only that, but as the pigs grow, they drink more, so the pattern repeats, but with increasing values at the same time, like our plus 0.28 trend in the previous example. And I can use the same two equations to estimate the water consumption at any chosen time t as I did before. For that, theta in this case contains 25 elements, where the first is the expected level of water consumption at time t, and the other 24 describe the changes expected at each hour of the day following the daily cyclic pattern. The system matrix G is also adapted to this model's needs and is composed by smaller submatrices. We can see on the top left a well-known group of numbers here, as that one will help calculate the effect of the daily growth of the pigs on the water consumption as a starting point, but that number will then be affected by the harmonic waves from the daily cyclic patterns to be applied to the theta component corresponding to each hour of the day in theta. Now the design matrix F also has an adapted shape, so it matches the needs of this model, so the whole thing can get quite complex actually. But throughout all that complexity, the model equations are still the same, and still only two. And it is because of that elegant simplicity that you need to understand matrices and how they operate with each other in order to understand dynamic linear models. Thank you for following this lecture, and you can find the links to the files for the exercise solutions and all that in the comments around this video. Thank you again.